Hi everyone, welcome back to another episode of Data Structures and Algorithm where I talk to you about my favorite DSA. And today's episode is going to be about, drumroll please, Dijkstra algorithm debunked. And as always, this is brought to you by your favorite P mentor, Lana. Okay, think about this. I need to get to my bestie's house, but the road that I usually take is so much traffic that I need to find a different path to get to there, a much more efficient one. So, okay, so for the sake of simplicity, I'm going to represent my map with a weighted graph like this, with A and F being my source node and my destination node, and in between, we have all the different nodes to represent different locations that we're going to visit during my trip. And as you can see, and suppose I'm driving an electric vehicle, I'm going to also have the weight of these um, edges on a graph to represent the amount of battery that I would need to travel from one node to another. Okay, as you can see, I'm using a directed acyclic graph, which just means that if you leave a node, you cannot go back to it. Okay, moving on. Okay, so how do we solve it in a large scale? So this guy named Dijkstra in just 20 minutes in 1956 came up devised this amazing algorithm that solved the exact problem which is discussed, and that's called the Dijkstra algorithm. So how do we use it? So first up, we're gonna update these nodes with the amount of the minimum distance that we required to get to them. And since we haven't visited any of them to begin with, I'm gonna initialize them with infinity. And since A is our starting destination for the source node, I'm gonna update A with 0. Okay, next I'm gonna start scanning for all of A neighbor, which in this case are B, C, and D, to see if there's any edges that can relax. And relaxing an edge just means that updating the the minimum distance at the node with, a shorter distance that you just discovered. In this case, I found out that 35 is much smaller than infinity, so I update C with 35, B with 5, and D with 40, so on and so forth. And next thing I need to do is I'll keep track of a predecessor list and a min-heap priority queue. And that just means that I'll keep track of these nodes B, C, D with the minimum distance required to travel to them, and then a predecessor list with A being the predecessor of B, C, and D. Makes sense, right? Okay, moving on. Next thing we need to do is popping off the top element in the min heap. In this case would be B. Okay, moving on to B, start scanning the AD and E, and as you can see, A is being colored red because since we already visited A before, we're not allowed to go back to A. Okay, moving on to B and D, relaxing these two edges, and then I'm gonna update D and E to our min heap and our predecessor list. As you can see, D was not in there before. I'm sorry. Okay, as you can see, D was 40, but since we just found a smaller number, this case is 25, update D, then the value of D in our priority queue, and then update D, B as the predecessor of D and E in our predecessor list. Okay, moving on, popping D off the queue, see that, relaxing the D and F, update the F to the predecessor in the min heap. Moving on, popping E off the queue, we can see that we cannot relax any of these edges. So just move on. Popping C off the queue, cannot relax any of these edges. And then since at the final destination, there's nothing we need to do anymore. Okay, so now that we have going through all of our nodes in the priority queue, and how do we find the shortest path for the predecessor list that we found? And the answer is tracing back all the way from the final destination to the source node. And in this case, I'll start with F, F trace back to D, D trace back to B, B trace back to A. And that, everyone, is my shortest path calculated by the Dijkstra algorithm. Woohoo! Okay, moving on to algorithm analysis. Time complexity, we have a know of V plus E times log of V, but bear with me while I explain this, okay? But promise it's not scary. Since we have V nodes, V number of nodes being extracted, and E edges being relaxed, each of them multiplied by the log of V from the heaps operation, that's gonna be log of V times the sum of V and E. Okay, sorry, forgot to mention, but V and E is respectively the number of vertices and edges in our graph. Then as of space complexity, much more simple. It's just an O to V because we're storing um, a priority queue of V nodes. Remember them? Yeah. Okay. Makes sense, right? Great. Okay, moving on. Oh, one thing that you guys need to keep in mind is that Dijkstra algorithm will fail if you use it with negative edges because it assumes that the first time I find about that path, that's already the best one. So it does not take into account negative numbers. So, Lana, then what do I do if I have a graph with negative edges? The answer is the Bellman-Ford algorithm, but that's for a different episode. Moving on to the coding implementation, I'm just going to breeze through this because I'm running out of time. But first up, we have a helper function to construct my adjacency list. Then my Dijkstra function, I'm going to use my helper function to create a adjacency list, create a priority queue, vector to keep up with the distance between V and the max distance, and then okay, and then I'm gonna have a while loop that just keep moving up, that just keep iterating until we go through all the nodes and just keep going when our min heap is not empty, and then popping out the first element in the heap every single time. And then for each of those top nodes, we're gonna scan through all of their neighbors to see if there's a shorter path than the one that we already recorded in there. And if there's a shorter path, we update it with the number that we recorded. And this might look scary, but I promise, super simple, super easy. It's just exactly what we did before. Okay, don't panic. I got you right here. And then, whoa, what is that? Oh yeah, that's my email, guys. So please do reach out to me if you have any questions. Like, oh my gosh, Lalan, your lectures are great. Or, oh my gosh, you're so fast. Like, there's so many things that you need to change. So if you have any questions, any feedback, concerns, or, you just want to hang out with me, please do reach out. And, that's it for today's episode. I love you guys so much. See you guys in another episode. You know, if this series ever got sponsored by Professor Aman Kapoor. So that's it for today. Bye, guys.